While you walk through the streets, drive through the city, or simply turn on the tap at home, a $22 billion empire operates silently beneath your feet. High-density polyethylene pipes, known by the acronym HDPE, form an invisible network that sustains modern life. Every drop of water that reaches you, every sewage system that functions flawlessly, every gas network that powers industries depends on this technology that few know about, but everyone uses daily. The global HDPE pipe industry moves figures that rival entire sectors of the economy. We are talking about a market that grows between 5 and 7% annually, driven by an insatiable demand for infrastructure. Expanding cities, developing countries, industrialized nations renewing old systems, all converge to the same point: the urgent need for modern, durable, and efficient piping. What appears to be just plastic hides decades of engineering, billions in investments, and a production chain that employs millions of people around the world. Unlike the metal pipes that dominated the 20th century, HDPE revolutionized how we transport liquids and gases. Its corrosion resistance, structural flexibility, and lifespan exceeding 50 years completely transformed the infrastructure sector. Governments invest fortunes replacing old systems with this technology. Private companies bet billions on increasingly larger and more automated factories. The result is an industry that never stops growing, even during periods of global economic crisis. The manufacturing process of these pipes happens in colossal facilities, where machines the size of buildings operate 24 hours a day. Each factory can produce thousands of kilometers of piping per year, serving projects ranging from small residences to national infrastructure megaprojects. The production scale is so impressive that a single extrusion line can consume tons of raw material per hour, transforming plastic pellets into pipes that will cross continents. But what makes this market so valuable is not just the production volume. It is the combination of advanced technology, growing demand, and the inevitable replacement of obsolete systems. While iron and copper pipes rust and degrade, HDPE remains intact for decades. This durability translates into savings for governments, companies, and ultimately for you. The invisible empire beneath our feet is not just an engineering matter, it is a silent economic revolution redefining how we build the modern world. Everything begins with small white or translucent pellets, each the size of a grain of rice. These high-density polyethylene pellets are the heart of a multi-billion-dollar industry. Produced from petroleum through complex chemical processes, these pellets pass through specialized refineries before reaching pipe factories. The global HDPE resin market alone moves tens of billions of dollars annually, feeding not only pipe production, but also packaging, containers, and industrial components. Resin quality directly determines final product quality. Manufacturers invest millions in supply contracts with petrochemical companies, guaranteeing raw material with rigorous specifications. Each resin batch undergoes tests for density, melt flow index, and molecular resistance. A minimal variation in these properties can compromise thousands of meters of piping. Therefore, factories maintain internal laboratories that constantly analyze samples, ensuring each pellet meets international standards. Transporting this raw material is a complex logistical operation. Trucks and trains loaded with tons of pellets circulate daily between petrochemical plants and pipe factories. Some producers opt for gigantic storage silos capable of storing weeks of production. Others work with just-in-time systems, receiving daily deliveries to keep production flowing without interruptions. Each strategy has its costs and benefits, but all share the same goal: ensuring production lines never stop due to lack of material. Besides virgin resin, the industry also incorporates recycled material in certain applications. Pipes used in temporary or less critical projects can contain percentages of recycled HDPE, reducing costs and environmental impact. This practice has grown as environmental regulations become more rigorous and pressure for sustainability increases. Companies that master HDPE recycling gain competitive advantage, reducing dependence on virgin resin and attracting customers concerned about carbon footprint. Resin price fluctuates according to the oil market, creating a constant game of financial planning for manufacturers. When the oil barrel rises, resin becomes more expensive, pressing profit margins. When it falls, competition intensifies and pipe prices may decrease. This volatility forces companies to maintain sophisticated hedging strategies and long-term contracts. In the end, these small pellets that seem so simple carry with them all the complexity of a global commodity chain worth billions. The factories that produce HDPE pipes are true industrial cathedrals. Warehouses with tens of thousands of square meters house extrusion lines that extend for more than 100 meters. These colossal machines, which can cost millions of dollars each, represent the apex of manufacturing engineering. Companies invest fortunes not only in purchasing equipment, but also in necessary infrastructure, robust electrical systems, cooling towers, automated conveyors, and climate-controlled storage areas. Each production line functions as an integrated organism. At the entrance, pneumatic silos feed the extruder with resin. Sensors constantly monitor flow, adjusting feeding speed to maintain stable production. The extruder itself is a massive cylinder equipped with electrical resistances that heat the resin to melting point. Inside this cylinder, an endless screw rotates continuously, mixing and pushing the melted material toward the die. Temperature is controlled with precision to degrees Celsius, as any variation can compromise the molecular structure of the pipe. The die, or matrix, is where the pipe gains its shape. Manufactured in special steel and polished with micrometric precision, the die determines the external diameter of the pipe. The molten material is forced through the die under high pressure, emerging as a continuous cylinder of still malleable plastic. At this moment, the pipe enters a vacuum tank that maintains its exact dimensions while cooling begins. Water circulates through channels around the pipe, solidifying the HDPE gradually from outside to inside. The automation of these factories has reached impressive levels. Computerized systems control every aspect of production: temperature, pressure, extrusion speed, cooling rate, wall thickness. Operators monitor digital panels displaying hundreds of parameters in real time. When something deviates from standards, alarms sound and automatic adjustments take action. In some modern factories, robots manipulate finished pipes, stacking them with millimetric precision and preparing them for shipment without human intervention. But even with all this technology, the human factor remains essential. Specialized technicians adjust machines, perform preventive maintenance, and solve problems that no computer can anticipate. Engineers develop continuous improvements in processes, seeking to increase efficiency and reduce waste. The combination of steel giants and human expertise is what allows these factories to operate 24 hours a day, 7 days a week, producing the pipes that sustain global infrastructure. The extrusion process is a precise dance between heat, pressure, and time. When HDPE pellets enter the extruder, they encounter a hostile environment, temperatures exceeding 200 degrees Celsius. Under this intense heat, the solid polymer transforms into a viscous mass, almost liquid. The endless screw inside the extruder not only pushes this material, but also mixes it, guaranteeing perfect homogeneity. Any air bubble, any impurity, any temperature variation can create weak points that will compromise the pipe years later. As the molten material is forced through the die, it emerges as a continuous hollow cylinder. At this critical moment, the pipe is still malleable, almost like hot rubber. This is where the calibration system comes into action. Vacuum tanks apply negative pressure on the external surface of the pipe, pressing it against refrigerated molds that define its final diameter with millimetric precision. Simultaneously, compressed air is injected inside the pipe, maintaining its perfect circular shape and preventing collapse during cooling. Cooling is perhaps the most delicate stage of the entire process. If it happens too fast, internal tensions accumulate in the material, creating fragility points. If too slow, production decelerates and costs increase. Engineers spend years optimizing this balance. Cooling baths extend for dozens of meters, with water circulating at controlled temperatures. Infrared sensors continuously monitor the pipe surface temperature, adjusting water flow to maintain uniform cooling along the entire length. After complete cooling, The pipe passes through automated measurement stations. Lasers scan the external diameter. Ultrasonic sensors verify wall thickness. High-resolution cameras inspect the surface for imperfections. Any deviation from specified parameters triggers alarms. Defective sections are automatically marked and will be removed at the cutting stage. This continuous inspection guarantees that only perfect pipes reach customers, maintaining factory reputation and avoiding catastrophic field failures. Finally, the continuous pipe is cut into standardized lengths. Automated saws perform perfect perpendicular cuts, generally in sections of 6 or 12 meters, depending on customer specifications and transportation limitations. Ends are beveled, identifications are printed on the surface, and in some cases, connections are pre-installed. What began as small plastic pellets is now a sophisticated industrial product, ready to be buried under streets, installed in buildings, or laid across fields, carrying water, gas, or other fluids for decades without failing. In an industry where failures can mean environmental disasters, urban floods, or gas explosions, quality control is not optional, it is obsessive. Each factory maintains laboratories equipped with instruments costing hundreds of thousands of dollars. Specialized technicians collect pipe samples at regular intervals, subjecting them to batteries of tests that can take hours or even days. These tests simulate decades of use in a matter of hours, applying extreme pressures, varied temperatures, and hostile environmental conditions. The hydrostatic pressure test is one of the most critical. Pipe samples are sealed at the ends and filled with water. Pumps gradually raise internal pressure to levels far superior to what the pipe will face in normal use. Technicians observe whether there are deformations, leaks, or ruptures. Pipes that fail this test reveal problems in the manufacturing process that need immediate correction. Entire batches can be rejected if samples do not reach required standards, representing significant financial losses but guaranteeing absolute safety. Tensile tests evaluate the mechanical resistance of the material. Special machines stretch HDPE samples to the breaking point, measuring how much force the material supports before failing. This data is compared with rigorous technical specifications established by international standards. Variations in resistance can indicate problems with resin, inadequate processing temperatures, or material contamination. Each anomaly is thoroughly investigated, with teams tracing the problem to its origin in the production chain. Long-term durability is tested through accelerated aging. Samples are exposed to intense ultraviolet radiation, extreme thermal cycles, and aggressive chemical environments. The objective is to simulate decades of exposure in a matter of weeks. Pipes that will be buried need to resist soil pressure, constant humidity, and contact with chemical substances present in the earth. Pipes for industrial applications face even more severe tests, including resistance to acids, bases, and organic solvents. Besides destructive tests, visual and dimensional inspections happen continuously on the production line. Trained operators examine pipe surfaces for marks, deformations, or discolorations. Measurement instruments verify whether diameter and wall thickness are within specified tolerances. Traceability systems record each batch produced, allowing any problem identified in the field to be traced to the exact moment of manufacture. This level of control transforms HDPE pipe production into an exact science, where nothing is left to chance. Producing thousands of kilometers of pipes is only half the challenge. The other half is delivering these pipes to customers scattered across entire continents. The logistics of the HDPE industry is a military operation on a commercial scale. Storage yards the size of football fields accumulate organized stacks of pipes, each identified by barcode recording diameter, thickness, production batch, and final destination. Forklifts and cranes move tons of material daily, loading trucks departing toward construction sites across the country. Road transport dominates local and regional deliveries. Specially designed trucks carry pipes up to 12 meters in length, tied with high-resistance straps to prevent displacement during transit. Specialized drivers navigate narrow roads, muddy construction sites, and congested urban centers, delivering loads that can weigh dozens of tons. Each trip is planned with precision, considering weight restrictions on bridges, traffic schedules, and weather conditions that may affect cargo safety. For international or large-scale projects, Maritime transport enters the scene. Containers filled with HDPE pipes cross oceans, departing from factories in Asia, Europe, or the Americas toward emerging markets in Africa, the Middle East, or Oceania. Cargo ships transport thousands of tons of piping in a single voyage, reducing unit costs and enabling projects in remote regions. Specialized ports possess infrastructure dedicated to pipe handling, with long-reach cranes and temporary storage areas protected from weather. Rail transport offers an efficient alternative for long terrestrial distances. Platform wagons carry large-diameter pipes that would be impractical on highways. Freight trains cross continents, connecting factories to infrastructure projects in remote regions. This modality is especially important in countries with continental dimensions, where the distance between production and consumption can exceed thousands of kilometers. The combination of different transport modalities creates a complex logistical network that maintains constant flow of pipes wherever needed. But logistics does not end at delivery. Manufacturers maintain technical support teams that accompany pipe installation, ensuring they are handled correctly and installed according to specifications. Improperly stored pipes can suffer permanent deformations. Incorrect installations can create stress points that will lead to premature failures. Therefore, investment in logistics includes training installation teams, supplying specialized equipment, and post-sale follow-up. The journey of an HDPE pipe from factory to its final destination underground is an operation that moves billions and employs thousands of professionals around the world. The HDPE pipe market is not uniform. Different applications generate different profit margins and require different levels of specialization. The potable water segment is the largest by volume, representing billions of dollars in annual sales. Municipal governments, sanitation companies, and public infrastructure projects consume massive quantities of piping for distribution networks. These contracts generally involve competitive bidding, where price is the decisive factor, compressing margins but guaranteeing gigantic volumes that justify investments in productive capacity. The natural gas sector offers more attractive margins but demands rigorous certifications and even higher quality standards. Pipes for gas transport need to withstand higher internal pressures and pass through extremely severe safety tests. Companies that dominate this niche charge significant premiums over conventional pipes, justified by the responsibility involved. A failure in a gas network can result in explosions, deaths, and multi-million-dollar lawsuits. Therefore, only manufacturers with proven track records and international certifications manage to enter this lucrative market. Industrial applications represent another high-value segment. Mining companies use HDPE pipes for transporting mineral slurries, where abrasion resistance is critical. Chemical industries need piping that resists corrosive substances that would destroy metals in weeks. Large-scale irrigation farms demand complete water distribution systems, including pipes, connections, and valves. Each of these niches has its technical particularities and specialized suppliers, creating opportunities for companies that invest in research and development. The replacement market is a growing goldmine. Cities around the world face the aging of their water and sewage networks, installed decades ago with materials that are now failing. Corroded iron pipes, asbestos cement, prohibited for health reasons, old generation PVC that no longer meets current standards, all need to be replaced. Governments allocate billions in infrastructure modernization programs, and HDPE is the preferred choice for durability and ease of installation. This replacement market will continue growing for decades, guaranteeing stable demand for the industry. Geographically, the largest markets are in regions with massive infrastructure investments. Asia-Pacific leads in absolute volume, driven by accelerated urbanization and government sanitation projects. North America and Europe represent mature markets focused on replacement and modernization. The Middle East and Africa emerge as growth frontiers, where water scarcity and economic development create explosive demand for efficient distribution systems. Companies that strategically position their factories in these regions capture market share and maximize returns on investment. For decades, cities depended on cast iron, galvanized steel, and copper pipes for their water networks. These materials dominated the 20th century but brought chronic problems: corrosion, mineral deposits, leaks, and limited lifespan. Streets were constantly excavated for repairs. Maintenance costs consumed municipal budgets, and water losses through leaks reached alarming levels. The arrival of HDPE changed this scenario dramatically, offering an alternative that surpasses traditional materials in virtually every aspect. Corrosion resistance is perhaps the most significant advantage. While metal pipes rust when exposed to moisture and chemical substances present in soil, HDPE remains chemically inert. It does not matter if the soil is acidic, alkaline, or contains aggressive salts. The polymer does not react. This property translates into a lifespan that can exceed 50 years without significant degradation. Cities that install HDPE networks today can expect decades of problem-free operation, drastically reducing maintenance and replacement costs. Material flexibility revolutionized installation techniques. HDPE pipes can be bent in relatively wide radii without need for connections, simplifying projects and reducing potential failure points. This characteristic is especially valuable in irregular terrain or installations that need to circumvent obstacles. Additionally, material lightness facilitates transport and field handling. Smaller teams manage to install more piping in less time, reducing labor costs and minimizing urban traffic disruptions. Modern installation techniques take maximum advantage of these properties. Horizontal directional drilling allows installing pipes under rivers, roads, and dense urban areas without open excavation. Specialized machines drill underground tunnels and pull HDPE pipes through them, leaving the surface untouched. This technology reduces environmental impacts, pavement restoration costs, and inconvenience to the population. Projects that would take months with traditional methods are completed in weeks, saving time and money. Pipe joining also evolved. Thermofusion systems create connections that are as strong as the original pipe, eliminating leak risk at joints. Fusion machines heat pipe ends to the softening point and press them together, creating a permanent molecular bond. There is no need for sealing rings, glues, or additional components that can fail over time. The result is a monolithic piping network without weak points, capable of withstanding high pressures and ground movements without compromising its integrity. This silent revolution is rebuilding global infrastructure, one pipe at a time. The global HDPE pipe market is dominated by a relatively small group of manufacturers operating on a continental scale. These companies invest billions in productive capacity, research and development, and geographic expansion. Some are divisions of petrochemical conglomerates that control the entire chain, from resin production to finished pipe. Others specialize exclusively in pipe extrusion, buying resin on the market and focusing on operational efficiency and process innovation. Competition is intense, but there is also room for collaboration. International technical standards are jointly developed by industry associations that bring competitors together. These standards guarantee that pipes from different manufacturers are compatible and meet minimum quality and safety requirements. Companies that actively participate in these standardization processes gain influence over the industry's future, shaping specifications that favor their technological capabilities and creating entry barriers for new competitors. Mergers and acquisitions constantly reshape the competitive landscape. Large manufacturers buy smaller competitors to gain access to new geographic markets or specific technologies. Regional companies consolidate to compete with global giants. Financial investors identify opportunities in well-positioned manufacturers, injecting capital for expansion in exchange for equity participation. Each strategic move is calculated to capture a larger share of a market that continues growing, driven by fundamental infrastructure needs. Verticalization is a common strategy among sector leaders. Companies that control from resin production to final pipe installation capture margins throughout the value chain. This integration also offers competitive advantages in terms of quality control, supply security, and ability to offer complete solutions to clients. Large-scale projects frequently prefer suppliers who can deliver not only pipes, but also connections, valves, installation equipment, and integrated technical support. Innovation is the battlefield where leaders separate from followers. Companies invest millions in research centers that develop new HDPE formulations with improved properties. greater resistance to high temperatures, better performance in high-pressure applications, additives that increase UV resistance for exposed pipes. Patents protect these innovations, creating temporary competitive advantages that justify premium prices. In the end, the $22 billion market rewards those who not only produce pipes, but constantly reinvent what those pipes can do. The HDPE pipe industry faces a modern paradox. Its products are essential for sustainable infrastructure, but they are made from petroleum-derived plastic. This tension drives sustainability innovations that are transforming the sector. Manufacturers invest in recycling programs that collect used pipes at end of life, grind them into pellets, and reintroduce them into production. Although not all applications accept recycled material, many can incorporate significant percentages without compromising performance. Energy efficiency of modern factories improved drastically in recent decades. Heat recovery systems capture thermal energy that would be wasted and reuse it in the extrusion process. High-efficiency electric motors reduce energy consumption. LED lighting and intelligent automation decrease operational costs while reducing carbon footprint. Some factories invest in solar or wind energy, seeking carbon neutrality in their operations. These initiatives are not just marketing, they are responses to growing regulatory pressures and customer demands for sustainable products. HDPE durability is, in itself, an environmental benefit. Pipes that last 50 years or more mean fewer replacements, fewer excavations, less material consumption, and less waste generation. When compared with metal pipes that need replacement every 20 or 30 years, HDPE significantly reduces environmental impact over the complete life cycle. Life cycle analyses show that, despite being plastic, HDPE can have a smaller environmental footprint than traditional alternatives when all factors are considered. Leak reduction is another positive environmental impact. Water networks built with old metal pipes lose alarming percentages of treated water through leaks. In some cities, losses exceed 30% of distributed volume. HDPE pipes with thermofused joints eliminate virtually all leaks, conserving precious water resources. In regions where water is scarce, this efficiency is not just economic, it is a matter of survival. However, challenges remain. Improper disposal of pipes at end of life is still a problem in many regions. Collection and recycling programs do not exist in all markets, especially in developing countries. Dependence on petroleum as raw material links the industry to a fossil commodity, although research in bio-based polymers offers hope for future alternatives. The path to a truly sustainable industry is long, but the billions invested in innovation and growing pressures for environmental responsibility are accelerating transformation. Despite robust growth, the HDPE pipe industry faces significant challenges that can impact its trajectory. Oil price volatility directly affects resin cost, creating financial uncertainty for manufacturers and customers. When oil soars, infrastructure projects can be postponed because budgets cannot accommodate new prices. When it plummets, manufacturers who bought expensive resin face competitive pressure from competitors with cheaper inventories. This economic roller coaster demands sophisticated financial management and capacity to absorb fluctuations without compromising operations. Competition from alternative materials is constant. PVC pipes, although technically inferior in many applications, are cheaper and dominate price-sensitive segments. Polypropylene pipes gain space in high-temperature applications where HDPE has limitations. Composite materials promise to combine the best properties of different polymers, potentially creating superior products. HDPE manufacturers need to constantly demonstrate value, invest in innovation, and defend their market position against these challengers. Increasingly rigorous environmental regulations pressure the industry. Governments implement taxes on plastics, require minimum percentages of recycled material, or impose restrictions on petroleum-derived products. Although many of these regulations target disposable plastics, the pipe industry is not immune. Companies need to invest in compliance, develop products that meet new standards, and effectively communicate the long-term environmental benefits of HDPE. Those who do not adapt may lose access to important markets. Global productive capacity grew rapidly, creating overcapacity risks in some markets. When many manufacturers simultaneously invest in new factories, supply can exceed demand, triggering price wars that destroy profit margins. This phenomenon is especially problematic in emerging markets, where optimistic growth projections do not always materialize as expected. Companies that expand aggressively may find themselves with factories operating below capacity, burning capital without generating adequate returns. Finally, dependence on large infrastructure projects creates vulnerability to political and economic cycles. Government changes can cancel ongoing projects or redirect investments to other priorities. Economic crises freeze public spending, paralyzing bidding and postponing works. Manufacturers who depend excessively on government contracts face concentrated risk. Geographic and market segment diversification is an essential strategy to navigate these uncertainties. The $22 billion empire is powerful, but it is not invulnerable. The future of the HDPE pipe industry is being shaped by trends that go far beyond simple plastic extrusion. Digitalization is transforming how pipes are designed, manufactured, and monitored. Sensors embedded in piping allow real-time monitoring of pressure, flow, and structural integrity. Internet of Things systems connect entire water networks, detecting leaks instantly and optimizing distribution. This convergence between physical infrastructure and digital technology creates opportunities for manufacturers who master both worlds. Three-dimensional printing of components begins to impact the sector. Although it is not yet viable to print large-diameter pipes, customized connections, special valves, and complex adapters are already produced on demand. This technology reduces inventory needs, allows extreme customization, and accelerates new product development. As three-dimensional printers become larger and faster, it is possible that in the near future entire pipes will be printed at the installation site, eliminating transportation logistics. Smart materials represent another frontier. Researchers develop polymers that change color when exposed to specific chemical substances, alerting about contamination. Nanometric additives increase mechanical resistance without adding weight. Self-healing formulations can automatically seal small damages, further extending pipe lifespan. These innovations are in early stages, but demonstrate that tomorrow's HDPE will be much more sophisticated than today's. Expansion into new markets will continue driving growth. Developing countries invest billions in basic water and sanitation infrastructure. Arid regions implement massive desalination and water distribution systems. Precision agriculture demands increasingly efficient irrigation networks. Each of these applications represents billions of dollars in opportunities for HDPE pipe manufacturers. Companies that establish early presence in these emerging markets will reap rewards for decades. Sustainability will cease being a competitive differential to become a basic requirement. Customers will demand total transparency about carbon footprint, resin origin, and recycling practices. Manufacturers who do not adapt will lose access to public bidding and corporate contracts. Those who lead the transition to circular production models, where used pipes become raw material for new pipes, will dominate the future market. The invisible empire beneath our feet will continue growing, evolving, and reinventing itself, sustaining the infrastructure that makes modern life possible. $22 billion today can easily transform into 30, 40, or 50 billion in the coming decades, as the world recognizes that the foundation of everything we build begins with what is buried beneath our feet.